Hello, my name is Konstantin Dmitriev. I'm presenting some results made in the Laboratory of Inverse Scattering Problems in Acoustics of Moscow State University. In my report, I'm going to consider so-called scattering coefficients and the calculation of the acoustical field inside metamaterials and propose methods of designing this media. So when we talk about metamaterials, there are at least two problems. The first problem is how to create a medium with certain properties. There are several methods based, for example, on transformation acoustics or picking effective medium parameters. The second problem is how to calculate the field inside such a metamaterial. And here come, for example, finite element methods or scattering theory methods. In this presentation, we will discuss the possibilities of the scattering theory methods and their application to metamaterials in acoustics. We will begin with a short introduction and definitions of scattering theory. Then we will talk about both the direct problem of acoustical field calculation in a metamaterial and the inverse problem of creating a metamaterial structure. Now let's consider a finite size inhomogeneity R. It is placed in the homogeneous background medium. The wave field is produced by primary sources phi, and it satisfies the Helmholtz equation and Sommerfeld's conditions at infinity. The Helmholtz equation looks like this. Here P is the acoustic pressure, ρ is the medium's density, K is the wave number, and phi are the field sources. The equation has two solutions denoted by plus and minus signs. They correspond to the retarded and advanced case. With the well-known substitution, this equation can be written in this form. On the right, we can see primary sources as well as secondary sources. Secondary sources are proportional to the total field in each point and the scatter function in the same point, which is written here on the slide. The total field in the medium can be represented as a sum of the incident field and scattered field. The incident field is the solution of the homogeneous Helmholtz equation. And the scattered field is just the difference between total and incident field. The scattered field is produced by all secondary sources. Using all these facts together, we can write the solution in the form of the Lippmann-Schwinger equation, which means that the total field is a sum of the incident field and all fields produced by every secondary source. We will consider the two-dimensional case here, and the three-dimensional case is similar. Now let gamma be the circle containing the inhomogeneity. We will consider the case in which there are no primary sources inside gamma. It is important. The scattered field satisfies the homogeneous Helmholtz equation outside gamma. So it can be expressed in the form of a multiple series with Hankel functions. Coefficients B here depend on the primary source configuration and on the scatter function. The incident field satisfies the Helmholtz equation with no primary sources, but inside gamma. So it can be expressed in the form of a multiple series with Bessel functions. Coefficients phi here depend on the primary source configuration only. As the linear acoustics is studied, the coefficients phi and b are related to each other with the scattering matrix phi. This matrix describes all the multiple scattering processes inside the inhomogeneity. It is important that in some cases, this matrix has a simple diagonal form. It happens if the inhomogeneity is symmetric or has a small wave size. The case of small wave size inhomogeneity is very important because this inhomogeneity represents a metamaterial element. In most cases, it is sufficient to consider only monopole and dipole terms. So the matrix He includes only two scattering coefficients, beta 0 and beta 1. For example, it can be shown that if we have the density inhomogeneity of small wave size, it produces the dipole scattering field. And if we have the inhomogeneity of compressibility, it produces the monopole scattering field. The scattering coefficients for retards and advanced waves are not independent. It can be shown that a relation exists between them. Also, in the case of no attenuation, they are complex conjugated. We can introduce the amplitude and phase of scattering coefficients. And finally, we derive the relation between amplitude and phase of each coefficient. We can draw the scattering coefficients on the complex plane, and we can see that they form a circumference omega. This fact is very important. Using only phase C, we can describe all scattering processes inside an inhomogeneity. And you can see that geometrically C is just an angle between 0 and minus p. If attenuation exists, corresponding coefficients lie inside the circumference. Now let's talk about the direct problem of calculating fields inside the metamaterial based on multiple scattering theory. The considered approach is known as null field method. We'll consider the metamaterial which elements can be put inside non-overlapping circles like this. For example, here we have a hexagonal grid with inhomogeneities of square form. The grid may not be regular, and the metamaterial elements may also not be equal. So this model describes many metamaterial constructions. However, there are special cases that are not considered. For example, here we have a square grid with square inhomogeneities, and the circles do intersect. So this case is not considered. The primary sources are located outside the grid. Let's consider the element with the number q. The incident field can be expressed as a series of Bessel functions, like we did before for a single inhomogeneity. We introduce the vector phi double prime of expansion coefficients. The field scattered by the q element can be expressed as a series of Hankel functions. This also looks like the relations for single inhomogeneity, and we introduce the vector b of expansion coefficients. The difference now is that we must take into account all the fields scattered by other elements. The sum of these fields can also be expressed as a series of Bessel functions, as the sources lie outside the circle gamma q. And here we introduce the vector phi prime of expansion coefficients. Putting it all together, we have the algorithm. First, we need to build circles around each metamaterial element. Second, we use the expansions of fields into a series of cylindrical functions. Third, the coefficient vectors are related with scattering matrices, which may or may not be the same for every metamaterial element. And fourth, we use some addition theorem to relate the expansions centered at different points of the metamaterial grid. This algorithm can finally be written in the form of a discrete Lippmann finger equation. Here, the green function depends only on the grid itself. The scattering matrices depend only on each element construction. The algorithm has advantages and disadvantages. Not all configurations of metamaterials can be modeled, and sometimes it can be difficult to calculate scattering matrices, but it can be good for a metamaterial study since the number of equations is reduced. This direct algorithm can be helpful as a part of the inverse problem of the creation of metamaterial with certain properties. Such an inverse algorithm includes the following. First, we choose the grid geometry and parameters. Second, we select scattering matrices and try to get the effect. The direct algorithm is very helpful here since it is fast. Also, it is important that scattering coefficients have a limited set of values, so we don't need to test an infinite number of these values. The third step is to find the physical properties of the metamaterial element to have the found scattering matrix. This is the most complicated step. The first way of doing this is to solve the inverse scattering problem. And to do this, we use the algorithm invented by Roman Novikov and studied in our laboratory. The Novikov algorithm is the functional approach for reconstruction of the scattering function b based on the scattering amplitude f. It gives a precise solution for weak and minimum strength scatters and contains no iterations. This is one of the best methods to solve the inverse scattering problem. We have tested the Novikov algorithm for different scatters. For example, the results of monopole scatters are presented. Corresponding points are marked on the circumference omega. The graphs represent scatter function central cross sections. The red lines correspond to the ideal solution, and blue lines are the results of Novikov reconstruction. The ideal solution is a solution which first corresponds to the desired scattering coefficient, and second, its cool special spectrum lies inside the ball with a radius of doubled wave number. The physical meaning of this is that we cannot reconstruct the details of the scatterer, which are smaller than a quarter of a wavelength. This is the diffraction limit. We can see that the reconstruction is good almost everywhere, except for the left down part of the circumference omega. The result here is a high amplitude narrow peak. Its width is less than allowed by the diffraction limit, and the spatial spectrum of this solution is wide. As a criteria for the quality of reconstruction, therefore, we can consider the fraction of the spatial spectrum that lies within the doubled wave number range and approximately corresponds to the correct reconstruction of the scatters. We modeled this for a wider range of scattering coefficients, including the existence of attenuation inside the circle, or even non-physical case of amplification, which is outside the circle. It can be seen that the proportion drops sharply in the lower left part of the circle. The reconstruction of dipole type inhomogeneities is much poorer. The part of the spectrum outside the two wave number range for them may even be predominant, as can be seen from the legend on the right. So it is preferable to use the right half of the circle when trying to build a metamaterial. As an illustration, we present a simple example of the metamaterial built with the proposed methods. Here is the grid of 8 layers with 30 scatters in each layer. We found the values of monopole and dipole scattering coefficients, at which there is no reflection from the metamaterial. It was done on the notebook with only 8 gigabytes of memory. And here on the graph, we can see the absence of reflected wave. Here it is almost zero. To test the system, we rotated the grid and also added more layers to it. In both cases, there is no reflection, so the impedance matching holds. With the Novikov algorithm, we reconstructed the scatter function. The resultant metamaterial element can be a small ring or a cylinder whose density and speed of sound differ from those of the background medium. However, this approach has fundamental disadvantages. First, we have to transform the scatter function and get the actual physical material to be used in the metamaterial construction. This is an additional problem. Second, even if we do this, we have to implement a smooth dependence of the material properties on coordinates. And this is hard and may be expensive. Third, if we look at the scatter function, we can see that the size of the metamaterial element is quite large, about half the wavelength. And it's impossible to make it smaller because it's the result of an inverse problem solution, and this solution is restricted by the diffraction limit. To overcome the difficulties, we proposed to use layered cylinders with a small radius. Model A consists of air, silicon, and copper. Model B consists of copper, silicon, and copper layers. We varied the radii and calculated the scattering coefficients. If only monopole and dipole coefficients were significant, they were drawn on the plot at the right. Here the S point corresponds to the scatter we wanted to use in the non-reflective material. We can see that some combinations of scattering coefficients are quite easy to reach with the proposed model. At the same time, other combinations are hard to reach. So to do it, we used a more complex model with 5 layers. We varied the materials and layer thicknesses, and finally we got such plots. On the left, you can see all the points we could reach, and on the right, there's a relative error for using this result. The error is not very big, and it can be further reduced if we apply gradient adjustments to radii. As a conclusion, the wave motion in the metamaterial can be described as a multiple scattering process. It is possible to significantly reduce the amount of computation by separating the problem into the one-element scattering problem and the problem of multiple scattering between elements. The scattering coefficients form the limited sets, and it is easy to go through them and find the values corresponding to the desired medium behavior. Scatter reconstruction by the solution of the inverse scattering problem has fundamental disadvantages, but it is possible to propose a metamaterial element model for almost every combination of scattering coefficients. Thanks for your attention.